Good afternoon. My name is Mark McDougall, and the title of my thesis is Design, Manufacture and Test a Solar Heat Engine Generator. So just to walk through the contents of the presentation, I'm going to talk to you about my introduction, aims and objectives, the preliminary, initial and current design methods, current progress, future progress to a Gantt chart, references I have used, and a demonstration hopefully at the end. Introduction. So what are the drivers for to design, to manufacture and test a solar heat engine? 5 drivers are the current global environmental and economical climate, relieving our dependency on fossil fuels, renewable energy source, and because we are all engineers, we need to make a living off this. A lot of funding is going into research and development into renewables and sustainable solutions, and this project falls under that renewable and sustainable solution. So it's our goal to research this closely. So the title is Design, Manufacture and Test Solar Heat Engine Generator. The 3 first words really define my 3 aims: to design, manufacture and test. What am I doing? A heat engine that's the heat input is solar, and the useful work output will be used for generation electricity. So as I said, the aims are design, build and test. Design objectives are to use numerical and analytical methods to understand and appreciate the losses that will be expected, and to design for efficiency and adequate operation. The build-in objectives are to make it mechanically simple, build with respect to the design for minimum losses, and to minimize any changes to the initial designs conceived by myself. The testing should be done in a manner that doesn't hinder the performance of the engine. The overall goal of testing is to compare the actual with the designed performance of the engine, and overall then to suggest design changes based on those errors I've experienced through testing. Preliminary design methods really is a theoretical and an analysis. It's really the literature review, and the method I used was to choose a heat cycle, analyze the heat cycle and the engine based on this cycle, the present, future and advantages of the cycle and the engine, and any different engine configurations. So the heat cycles I studied are the Carnot, Otto, Brayton, Rankine, Ericsson and Stirling heat cycle. Starting off with the Carnot cycle is an ideal cycle. And for those reasons, an engine based on the Carnot cycle is unachievable, so its uses are strictly for comparison and research only. The Carnot cycle it establishes a formula which is known as the Carnot efficiency, which is 1 minus the ratio between the lower temperature source and the higher temperature source. Moving on to the Otto cycle. The Otto cycle, as you may or may not know, is the cycle that the internal combustion, your car engine, is based on. The internal combustion engine has, well, in terms of solar capabilities, to put it in one word, the solar capabilities are complex. Because the IC engine heat source is internal, it's internal to the material boundaries. To focus solar radiation inside material boundaries is very complex. Efficiencies of the internal combustion engine are 25 to 35%, and the efficiency is proportional to K, the ratio of specific heats, and or C, the ratio of compression rates. The Brayton cycle is the cycle behind the gas turbine. The gas turbine has solar capabilities at high temperatures, and at high temperatures is really the key word, because it's a small-scale college fourth-year project. To achieve the high solar temperatures would be it's unachievable, I think. But if those high temperatures were achieved, it would see efficiencies of 35 to 40%, and the efficiency is proportional to, again, the K, the specific heat ratios, and or P, the pressure ratios. The Rankine cycle is the cycle behind the steam engine, which saw development through the Industrial Revolution. The solar potential for the Rankine cycle, well, to put it, there is potential for it. However, the high cost of the use of a compressor and a turbine hinders any more research into the Rankine cycle for a heat cycle for using solar for electricity generation. I, as a student, do realize the potential for the Rankine cycle to be used for solar generation. So I suggest for any future theses in this area, that the Rankine cycle is definitely a cycle to look into. The efficiency of the Rankine cycle is between 40 to 50%, and the efficiency is proportional to the efficiency you can achieve with your turbine and your compressor. The Stirling and Ericsson cycle has extremely high efficiency, one of the highest at 40 to 60%, and also what led me to my interest in the Ericsson and Stirling cycle is this use of regenerators. The regenerators is what is the modern version of the economizer, which is what Robert Stirling first patented in 1816. The regenerator passes the air from the displacer cylinder to the power cylinder, and the ability of the regenerator to store and distribute heat energy is what makes the Stirling engine so efficient. The high efficiencies of 40 to 60% are because the efficiency of the Stirling and Ericsson cycle are based on the Carnot efficiency, as I said before, which is 1 minus the ratio of lower temperature source to higher temperature source. So looking at a cycle analysis and the engines the cycle produce, except the Carnot engine, because the Carnot engine cannot be achieved, looking at the Otto, the Brayton, the Rankine, the Ericsson and the Stirling cycle in terms of efficiency, cost, simplicity, research and solar applications, with 5 ranking the highest. The Ericsson and Stirling cycle on your right hand side has the highest score for its high efficiencies, low cost in designing and manufacturing, its overall mechanical simplicity, the abundance of research available and its potential for solar application. So we're now looking at the Ericsson and Stirling cycle. They both have the same thermal efficiency, which is the Carnot efficiency, and really to differ the Ericsson and Stirling cycle, the only difference really is on your left. The Ericsson cycle has isobaric regenerative process, while the Stirling cycle has isocharic regenerative process. So you're asking, why am I choosing the Stirling over the Ericsson? Well, through my research, the Ericsson cycle has a larger power-to-weight ratio compared to the Stirling engine. However, the Stirling engine has a large, diverse range of power output in terms of it can go to milliwatts. And for the Stirling engine, it can produce low power with a small-scale volume. The Ericsson cycle, it can produce that same power, but the volume needs to be greater. So for those reasons, the Stirling has better small-scale potential. Also, the Ericsson cycle is based closely on the alpha type Stirling configuration. You'll see in a diagram and you'll understand why I stayed away from the gamma, and it's also why I stayed away from the Ericsson cycle. So we're now looking at a Stirling cycle. The advantages of the Stirling engine based on the Stirling cycle is that it is silent operation because of its low vibrations. It can be used with multiple heat sources. It has a high achievable efficiency of 30 to 40%. That's the efficiency of the engine. The cycle has achievable efficiencies of 40 to 60%. It's mechanically simple because it has less seals, valves, and runs on virtually no lubricant. And my Stirling engine is working on no lubrication whatsoever. And in fact, it runs best when it's cleaned with soap and water, basically, than it would on lubrication. And through my testing as well, as a matter of interest, the Stirling engine can be running, and if I add lubrication, the engine will, 90% of the time, it'll stop running with the addition of lubrication. So another advantage is that it's long life in terms of years on how long it lasts, and also running time. It can run for days rather than hours. The diverse range in terms of power output, we can get a range from milliwatts to megawatts, and it is an air-independent engine in that it doesn't need an air source to run, which is advantageous to such people as NASA, as you'll find out now. So the future and present use. The present use at the moment is solar electricity generation. There is projects in America. In terms of Europe, there's a project in Spain for solar generation plants. In America, they're using parabolic dishes and incorporating a Stirling engine. As a matter of interest, in terms of Ireland, NTR, the National Toll Routes, which are the guys responsible for the toll booths in Dublin, they invested 63 million into a company in, I think it's Texas. The company's name is Tessera, and Tessera would be doing a lot of work with SES, Stirling Energy Systems, and the SES are responsible for the solar facility in California, which are looking to produce 850 megawatts of electricity with combined solar technologies such as parabolic Stirling engines, PV cells, and I think as well tower steam facilities. So combination of heat and power for isolated domestic areas is a future use. Multiple fuel sources for combustion is present. Waste heat and electricity for electricity generation is interesting. That it's around, but it needs to be incorporated more into, say, power facilities. It's advantageous in areas such as nuclear or steam electricity generating facilities, in that the waste steam or energy from those processes, Stirling stationary ground power unit can be incorporated into the waste heat. Biomedical power as well, very interesting in terms of the Stirling engine can be built to miniature scale, and this miniature Stirling engines can be used as a power source for artificial hearts or artificial organs, and also because Stirling engines, low temperature Stirling engines, LTDs, can run on as small as a temperature source as 0.6 degrees, which is very impressive, but also they have the capability of running for years continuously. And the common practice is to put in batteries as a power source for artificial hearts. But what happens in 3 years' time when your battery goes? You have to go back into surgery and get your battery replaced. Stirling engine has the advantage of running continuously for years. Cryo coolers is a concept of working a Stirling engine in reverse by adding mechanical work to the system, and the heat source, which would be the heat source, is mechanical if the Stirling engine was worked in traditional way, but in works in reverse, the heat source will become supercooled. Silent engines as well is advantageous, because if you can imagine, you're sitting in an airplane and you notice that you can't hear the gas turbines because your airplane is running, on a Stirling engine. Also, it's also advantageous because the Stirling engine would see improved efficiencies at the higher altitude, because the ambient air temperature is lower than sea level ambient air temperature. And also, vacuum electricity generation is seen development by NASA for extraterrestrial electricity generation, because they can, as I said, the Stirling engine is air independent. They can produce electricity in outer space using focused solar radiation as the heat source, or even on some scale micro radioactive substances as the heat source. So now going on to engine configurations, there's 3 basic engine configurations as developed by Schmidt in 1816, and they are the alpha, the beta, and the gamma. The alpha type configuration consists of 2 cylinders with 2 power pistons. Not shown in the diagram is a regenerator, which allows the working fluid to pass from cylinder to cylinder. As I said, the Ericsson engine is based on the alpha type configuration, and I stay away from the alpha type configuration because of the tolerances needed in producing not 1 but 2 power pistons. Moving on to the beta type configuration consists of 1 cylinder, 1 displacer piston, and 1 power piston. The displacer piston's role is to move the fluid from the high temperature source to the lower temperature source. It does not have an independent regenerator. The regenerator, in its simple terms, for the beta type is the space between the internal diameter of the cylinder and the external diameter of the displacer piston. And for these reasons, because it doesn't have an independent regenerator, I stayed away from the beta type, because I really wanted to study more the concept of the regenerator. So moving on to the gamma type configuration. The gamma type configuration consists of 2 cylinders, a power piston and a displacer piston. Again, the displacer piston's role is to move the fluid from one cylinder to the other, and it does have an independent regenerator, which is what I studied. So we're now looking at a Stirling type engine with a gamma type configuration. So now, analysing the Stirling engine, or the Stirling cycle with the gamma type configuration, in terms of looking at its internal volumes, its internal pressures and temperatures, we can get a rough guide of what's the work input needed and the work output. So looking at a work input of 35.3 joules to compress the fluid. Heat input for me, it's going to be solar input, looking at 10 kilojoules. The work output then 90 joules, usable work. So then the net work is the work output minus the work input, and we're looking at 55 joules of useful work, and a Carnot efficiency of 61 to 63%, which is on the higher scale of the 40 to 60% seen in the Stirling cycle. This is a robust PV work diagram of the cycle analysis. Not much really to show there. So we're moving on to the initial design methods, and there's two orders, the first order and the second order design methods. The first order looks at, we're now going to be looking at an engine rather than the cycle, and analysing a real engine and considering regenerator effectiveness and dead volumes, which are inevitably going to be in existence in a real engine. And the second order design methods looks at optimizing your engine, considering losses such as fluid friction losses, mechanical losses, reheat losses, and the following list there you can see. So on to first order design methods. The method of these is to establish reasonable dimensions and finding out what sort of performance characteristics are achieved from those dimensions, and then specify what sort of performances you would like to achieve, and then working back to get optimum diameters and dimensions really. So the PV work diagram based on my scale model, which is Pro-E drawings, which I don't have with me. We're looking at a PV work diagram which is much more realistic than the two previously I showed, and analysing the area between those curves using the trapezoidal method of integration. We're getting a work output of 19.3 joules. That's an analytical method. To use a numerical method, it's using the Schmidt equation, and there's a couple of different variations, and two I found useful is by Senf and Cook and Yardberg. The Senf Schmidt equation is getting a work output of 16 joules, and the Schmidt equation by Cook and Yardberg, which is the more accurate analysis, we're getting a work output of 24.3 joules per cycle. At 3000 RPM, that's 1.2 kilowatts, and I'm assuming 3000 RPM for adequate reasons. So you're thinking, 1.2 kilowatts. That's a lot of energy, and it is. And I did say the Cook and Yardberg equation is the more accurate one, but it's the most accurate because it requires further analysis. Further analysis of the Schmidt equation by Cook and Yardberg using what is known as experience factors, we can get the indicated work at 19.6 joules, which you can see is very similar to the trapezoidal method of integration, which calculated to be 19.3 joules. So at 19.6 joules at 3000 RPM, we're getting just under a kilowatt at 980 watts, and just over a horsepower at 1.3 horsepower engine performance. Looking at regenerator effectiveness, at a perfect regenerator, we're looking at the current efficiency of 60%. As the efficiency of the regenerator goes down, we're looking at engine efficiencies of around 12% before any losses are even considered. So the regenerator really is a critical part for the Stirling engine. Looking at dead volume percent, as the dead volume in relation to the total volume goes up, the engine performance and efficiency goes down, as seen in these sources here. Moving on to the second order design methods, we're looking at losses that are experienced. We're looking at total fluid friction losses due to the air traveling through the regenerator, the heater and the cooler. Very small losses, but it does all add up, and it's just really to note that the fluid friction losses as the fluid travels through the regenerator is greater than that experienced through the heater and the cooler. Looking at total mechanical losses, I'm looking at 26% loss in power due to mechanical losses. It's quite hard to calculate mechanical losses. There's a simple equation, they're not very accurate, of calculating mechanical losses, and it's the brake work minus the indicated work. The indicated work I threw up for you earlier. But also there's analytical methods of researching experimental data, looking at what kind of you want to really know what sort of crank mechanism you're going to looking at, and then looking at experimental data of what sort of mechanical losses a similar crank mechanism experienced through experimental data, and that's an analytical way of determining your mechanical losses. So now our output power is 724 watts. Then looking at the calculated basic heat input at 1,600 watts. Reheat losses at 17% losses. Therefore, the net heat input is 1,800 watts, thereabouts. Plus, I've yet to do calculations on shuttle conduction losses, gas and solid conduction losses, and the rest of the list you can see there. But at the moment, at a net heat input of 1,872 watts and an output power of 724 watts, the Stirling engine is looking at an efficiency of 38.7%, with further expected losses once I do further numerical and theoretical calculations. But at the moment, we're looking at 38.7% efficiency, which is on the higher scale of engine efficiency seen in the range of 30 to 40%. So everything's looking good at the moment. Current progress, just some concept drawings there. Might be a little difficult to see because I started off doing sketches. But if you can see, I started off looking at tubular regenerators on a very basic gamma type configuration. Moving on to Pro-E drones, then I'm on my second iteration here, where I incorporate a heater cap to increase the surface area exposed to the solar radiation, incorporating a cooling jacket around both cylinders to lower the lower temperature source, therefore increasing the efficiency. This is a gamma type configuration, and also replacing the tubular regenerator style to a manifold plate regenerator, where you'll see hopefully in the diagram in the next few slides that the regenerator will incorporate micro channels. So this is the third and current iteration of my Stirling engine. It incorporates a brass heater cap for increased surface area and improved thermal conductivity through the displacer piston wall. Displacer cylinder wall, sorry. It incorporates a stainless steel displacer cylinder and power cylinder. It incorporates two copper jackets for lowering the temperature of the cold temperature source. An aluminium power piston, more than likely. I'm still looking at data and research into the material suitable for a displacer piston. Ideally, I'd like to have a displacer piston made out of Pyrex glass, because it is the overall objective of the regenerator is to have low thermal conductivity, low fluid friction losses, and low weight. Pyrex glass would be ideal for this. However, I'd need to get it specially ordered. So I'm looking into alternatives. A very funny one, and I'm not sure of how it's going to work. We're looking at balsa wood as a displacer piston, though it's considered a hardwood. It is very soft, so it wouldn't actually be able to be hollowed out. You can actually carve balsa wood with a knife. It's that soft, though it's considered a hardwood. And it would also mean sealing the woods to protect it from the high temperatures experienced within the engine. The engine, by the way, will be operating at 755 Kelvin, which is about 600 degrees C, or 900 degrees C, 900 Fahrenheit for the Americans. Also, on the lower scale in terms of displacer efficiency, we have the obvious choice of aluminium or brass. But I want to try and stay away from that, try and get the displacer piston as working with optimum efficiency. The regenerator design here, as you can see, is a manifold plate where the fluid will be able to transfer between the cylinders, going through the microchannels. This is my current regenerator design. Moving on to performance concerns. Four things I'm concerned about really is that the calculations at the moment are still too idealized. The calculations are assumed that they assume that the expansion and compression stages of the Stirling cycle happen isothermally. However, the real engine will more than likely experience adiabatic compression and expansion. Also, at the moment, my calculations are calculated at the incoming temperature of the Fresnel lens, which will more than likely be higher than the metal temperature and be even higher than the gas temperature. So I really need to incorporate the gas temperature into my calculations rather than the incoming temperature of the Fresnel lens. Further analysis needs to be done on the optimum gas temperature and engine speed, because there is actually an optimum temperature and engine speed, which beyond this point the performance of the engine will decrease. So as I said, at 3000 RPM I could find out that the optimum speed is 1000 RPM. So I really need to incorporate that into my design calculations. Manufacturing, which will be done in the next month or so, manufacturing will inevitably lead to performance losses. And losses due to the conversion from the mechanical work to the electrical work will be seen as well, that I'm concerned about. Moving on to the system at the moment, Fresnel lens at the top will have solar radiation coming on to my Stirling engine. Stirling engine will be cooled to the copper jackets, which will be cooled in a radiator. The useful mechanical work will be attached to a motor. The motor will then be used for demonstrative purposes for LEDs or recharging batteries or a heating element. But in future projects, it could be, it has the potential to be sold onto the grid. Then I'll have a DAC set up, which will be measuring things such as temperatures, the rotational speed of the engine, torque output, and electrical output. And the DAC will be running into a laptop, which will be analysed. All the data will be analysed through LabVIEW. The Gantt chart at the moment, I've kept fairly well to it up to now. I have to slightly change what I'm going to be doing over the months. But in the next few months, I'm going to be obviously the push on getting solid Pro Engineer 3D drawings of my Stirling engine. Also ordering any special materials I need, and then my manufacturing stage, which will be hopefully about a month and a half, I'll be in the workshop manufacturing. I also need to design my testing facility, get that system figured out, and then once the manufacturing is done, to actually test my engine, and then to compare how the actual engine compares to the calculations I designed. References here, there's 6 of them. Some of them are used, which is only a proportion of what I have in my main thesis report, which I might be showing or might not be, but we'll see how it goes. And any questions? So the question is, where do I see the efficiency of the engine going? Well, if I go back to this slide here, you can see currently the efficiency of the Stirling engine is at 38.7% with further expected losses. Through further calculations of the losses, you can see here I still have to calculate for shuttle conduction losses. Shuttle conduction losses is due to the displacer moving from the high temperature source to the low temperature source, and as it does, the displacer is actually warming the cold temperature source and cooling the high temperature source, so I need to incorporate that. Gas and solid conduction losses, I need to understand and calculate how the thermal energy will transfer from the gas, the working fluid within the engine, and how it transfers to the solids within it, being the cylinder walls and the displacer. Pumping losses as well I need to incorporate, as the fluid is increasing and decreasing in pressure as it's flowing through the engine, because at the moment the calculations are all considered at a average working pressure of the engine. However, the pressure isn't constant within the engine. Heat exchanger evaluation will determine the efficiency of the high temperature source and low temperature source, and gas temperature losses as well. The gas temperature will not be as calculated at the 750 Kelvin and 293 Kelvin at the lower temperature source. So that's with those losses will probably bring the efficiency down to the low 30s. Then with manufacturing the actual engine, that will more than likely bring down the losses further to the low 20s, down another 10%. Then errors within calculations will probably bring the efficiency down to between 15% and 20%. And then converting the mechanical work into electrical work will probably bring the efficiency down to 10 to 15%. So that's where I really see the efficiency leading to overall. And if I did achieve an efficiency of 10 to 15%, I'd view that as a success. So your question is, what sort of tolerances do I need to work with? Well, once I go down to the workshop, there's 2 real critical parts that I need to focus on in terms of tolerancing. The power piston and the power cylinder, there needs to be tight tolerance there in order to create an adequate seal. And the gap between the external diameter of the power piston and the internal diameter of the power cylinder needs to be 0.01 of a mil. Therefore, the tolerances need to be between roughly about plus or minus 0.005 of a mil. Yes, the machines are capable downstairs. The machines are capable of getting tolerances down to that level. The second tolerances critical tolerances is where from the displacer piston, there's a crank rod coming out of the displacer piston onto the crankshaft, which is attached to the flywheel. So there needs to be a hole in the manifold plate. Now, from my analysis of the 2 Stirling engines, that's not a perfect seal, but I do need to create reasonably adequate seal. So there needs to be tight tolerances there, tolerances in terms of there needs to be a tight seal, and as well there can be very little friction, and in terms of the shafts have to be lined. That said, also the power piston needs to have a relative smoothness and flatness. It has to be has a straight cut in order to provide the seal. Also, that the grooves and the rings around the power piston as well will help achieve a solid seal. Also, secondary critical tolerance needs to be on the regenerator, because the regenerator fins need to be cut to about 1 mil in depth and 1 mil in width, which means cutting down into the material 0.5 of a mil and a width of 1 mil, which means cutting using a milling machine with ball to nose collet of a 1 mil diameter, which will probably take a lot of time. So they're really the critical tolerances I need to be working with down in the workshop.